Hi everybody. So in this next section 12.2 we're going to look at tests for independence and the homogeneity of proportions. So the objectives in this section will be to perform tests for independence, and then the second objective will be to perform a test for homogeneity of proportions. So let's look at the first objective here, to perform a test for independence. So basically the chi-squared test for independence is used to determine whether there is an association between a row variable and a column variable in a contingency table constructed from sample data. So this will kind of go back to a little bit to section 4.4 and contingency tables that we talked about before. And the null hypothesis is that the variables are not associated. In other words, they are independent. There's no association between the variables. And the alternative hypothesis in this case will be that the variables are associated or related to one another or dependent. So in other words, in a chi-squared independence test, the null hypothesis will always be that the variables are independent, and the alternative hypothesis is always that the variables are not independent. So the basic idea in testing these types of claims is to compare the actual counts to the counts we would expect if the null hypothesis were true. So in other words, if the variables were independent. If a significant difference exists between the actual counts and the expected counts, we would take this as evidence against the null hypothesis. Just to remind you also that if two events are independent, then the probability of E and F is equal to the probability of E times the probability of F. So we can use the multiplication principle for independent events to obtain the expected proportion of observations within each cell in the contingency table under the assumption of independence, and then multiply this result by the sample size in order to obtain the expected count within each cell. So as an example here, let's say that in a poll you have 883 males and 893 females, and they were asked if you could have only one of the following, which would you pick? Money, health, or love? And the responses are presented in the table you see below here, and it says determine the expected counts within each cell, assuming that gender and response are independent, right? So there's no overlap there. So first of all, you'll have to compute the column totals to see how many counts there are in each row and column, and then you'll get the total number of respondents here. So essentially you want to basically take the total in each column and divide by the total number, which is 1776, to get the relative frequency for each column and each row. And then again here you're dividing 1776 by itself, so you'll just get 1. And then so assuming gender and response are independent, we'll use the multiplication rule for independent events to compute the proportion of observations we would expect in each cell. So in this case, right, you would obtain these values, these proportions. What you would want to do then is take the total number times the expected proportions and calculate that, and then we will compare that to the observed proportions. So the value here in each cell, the 63.580, this value, this value, this value, and these values would be the expected outcomes. So the expected frequency then will be the row total times the column total divided by the table total. This is sort of a shortcut for computing the values we just obtained. So then OSABI then will represent the observed number of counts, similar to what we saw in section 12.1, and so we will use the same test statistic. I guess the one difference here is that the chi-squared distribution in this case will follow will have the number in each row minus 1 times the number of columns in each row minus 1 degrees of freedom. provided again that the following two conditions are met. That all expected frequencies are greater than or equal to 1, and no more than 20% of expected frequencies are less than 5, which is very similar to section 12.1. So the steps then for this procedure, which are outlined on the top of page 603 in that purple box, are, again, step 1 is to determine the null and alternative hypothesis. Remember, in this case, the null and alternative hypothesis will always be the same, that the row variable and column variable are independent, or the alternative hypothesis will be that the row variable and column variable are not independent, or in other words, dependent. So again, the alpha level should be given to you unless otherwise stated, right? It will be 0.05. And then calculate the expected frequencies. And then again, you should also verify the requirements for the test. Again, in most cases, you shouldn't really have to worry about that, but just to be on the safe side, you might want to verify that. Compute the test statistic, which is very similar to the what we did in section 12.1. And then either use the classical approach. In this case, remember the degrees of freedom is r minus 1 times c minus 1. So again, compare the calculated value to the value you look up in the table. And if the calculated value is greater than the value that you look up in the table, which is dependent on alpha, you would reject the null hypothesis. Or using the p-value approach, right, you can compute the actual probability, or get an approximation for the probability, again remembering that it's r minus 1 times c minus 1 degrees of freedom. And then if the p-value again is less than alpha, as is usual, right, we will reject the null hypothesis. And then don't forget to clearly state the conclusion so that non-statisticians can understand your results. So let's look at an example where we actually go through the chi-squared test for independence. So here we're using the data that we looked at before. So again, the null hypothesis will be that the gender and response are independent, and the alternative hypothesis will be that gender and response are dependent. Our level of significance in this case is 0.05. So we would calculate the expected frequencies just as we did before. And then in this case, and then these would be the observed statistics on the top, and these would be the expected frequencies, expected values on the bottom. Put those into your test statistic. So again, in this case, you're basically taking the difference between this and this and this and this, and then you're squaring each one of those differences and then dividing by the expected value and then adding those together. So if you calculate that, that will give you a chi-squared statistic of 36.82. And then at this point we have either again, we can use the classical or the p-value approach as you prefer. So using the classical approach, we need to look up the chi-squared value for our alpha value, which is 0.05. Remember, this will be for 2 degrees of freedom in this case, so that should give you a value of about 5.991. And since the test statistic in this case is greater than the critical value, we will reject the null hypothesis. Alternatively, using the p-value approach, we would want to look up the probability value for the calculated value. In this case, the p-value is less than the level of significance. Again, if you want to actually calculate the p-value, you might have to use some sort of technology like StatCrunch or something like that. So in this case, we would also reject the null hypothesis. So again, remember, you should get the same answer using the classical approach or the p-value approach. So one way you can do the problem to sort of double check your results is use the classical approach and then the p-value approach and check to see that you get the same answer in both cases. And then also, don't forget to state the conclusion in words, right? So in this case, the conclusion would be there is sufficient evidence to conclude that gender and response are dependent in this case. To see the response, to see the relation between response and gender, we will draw a bar graph of conditional distributions of response by gender, and recall that a conditional distribution lists the relative frequency of each category of a variable given a specific value of the other variable in the contingency table. So let's say we want to find the conditional distribution of response by gender for the data from the previous example. here it is reproduced below. We first compute the conditional distribution of the response by gender, and then here would be a graph of male versus female. And so if you look at what people value based on gender, this will give you sort of more of a breakdown. Okay, so that brings us to objective 2, which is to perform a test for homogeneity of proportions. In a chi-squared test for homogeneity of proportions, we test whether the different populations have the same proportion of individuals with the same characteristic. The procedure for performing a test of homogeneity are identical to those for a test of independence. So here's another example. So the following data here represents data collected by asking, would you tell me if you feel being a teacher is an occupation of very great prestige, based on the following years here. And we will test the claim that the proportion of individuals that feel being a teacher is an occupation of very great prestige is the same for each year at the 0.01 level of significance. So the null hypothesis will be that the three proportions are the same, and the alternative hypothesis will be that at least one of the proportions is different from the others, and again, in this case, the level of significance will be 0.01. So we calculate the expected frequencies, and since none of the expected frequencies are less than 5, the requirement is satisfied. Compute the test statistic as before by taking the difference between the observed and expected frequencies, squaring those and adding those together. Using the classical approach, again in this case we'd use 2 degrees of freedom. Remember alpha was equal to 0.01, so we'd get 9.210. So in this case, comparing this to the calculated statistic, since the calculated statistic is greater than the value we look up in the table, the critical value, we will reject the null hypothesis. Using a p-value approach, again we get this test statistic. So the p-value is less than the level of significance, so again we would reject the null hypothesis, again getting the same value, or same result that we would expect using the classical approach, and then just make sure you state the conclusion, right? So there is sufficient evidence to conclude that the proportion of individuals who believe that teaching is a very prestigious career is different for at least one of the 3 years. Now the only thing is it doesn't tell you which one of the 3 years is greater than the others, but it would, if you look back at the original data, it would seem like the proportion is going up over time, so one would assume it would be the 3rd year, but that may not be the case. So what we will look at then in the next chapter is ways for determining which one of the 3 proportions are different. Are they all different, or is only one of the proportions different? But we'll have to leave that for the next chapter. So, alright, well I hope that makes sense. If you guys have questions about anything, as usual, let me know.